Okay, to pick up where we left off on molecular orbitals, we were just talking about the overlap of s atomic orbitals to form sigma s molecular orbitals. And now what we're going to start with is the end-to-end overlap of p orbitals, leading to what are known as sigma p molecular orbitals. First of all, we have to mention something that we kind of mentioned in passing in the past, but never really did anything about. And that is the fact that p orbitals have two phases. You can think of it as being one phase up, one phase down, or one phase in, one phase out, or one phase left, one phase right. But the fact is that they have two different lobes, or two phases, if you want to call it that. And it's kind of like the peak and the trough of a wave in the wave function. And they are different, and it's kind of like the difference between constructive or destructive interference. It matters which lobes of the p orbitals are pointing towards each other when you try to form a sigma bond between them, or when you try to form a sigma molecular orbital between them. So if the same phases of the orbitals on neighboring atoms overlap end to end, then what you get is called a sigma p bonding molecular orbital. And so you've got the px orbital on one atom and the px orbital on the neighboring atom. And they come together with the way I've drawn it here, the unshaded lobes pointing towards each other. And once they meet and start overlapping, you get a sigma p molecular orbital, which is drawn something like this. Again, the book draws it better than I can, but the idea is that most of the most of the electron density is between the nuclei. These two big dots here, those would be the nuclei. And the little lobes that point outward and are shaded, those are sort of what's left of the lobes that were pointing outward when the atomic orbitals came together, the shaded parts. And they tend to get smaller while the parts of the orbitals between the atoms get bigger. That's sort of like constructive interference. On the other hand, something analogous to destructive interference would be if different phases or lobes of p orbitals on neighboring atoms overlap end to end. Then what you get is a sigma star p anti-bonding molecular orbital in that case. Okay, so I've drawn two p orbitals here on neighboring atoms. And in this case, the shaded lobe is meeting up with the unshaded lobe on the other atom. And the result would be a sigma star p anti-bonding orbital, because as you can see, a vast majority of the electron density is outside of the area between the two nuclei. And so this is a case where no bond will be formed between those two atoms. You can also have side-by-side overlap for p orbitals, and that leads to pi bonding, and also it leads to pi molecular orbitals. And as before, sometimes it leads to a pi bonding molecular orbital or a pi star anti-bonding molecular orbital. Again, the bonding molecular orbitals are lower in energy than the p orbitals from which they're derived, and the pi star anti-bonding orbitals are higher in energy than the p orbitals from which they are derived. Okay, the pi bond ends up having what's called a nodal plane along the axis between the nuclei. Because the axis between the nuclei, that's where the sigma bond is located. So the pi bond would be above and below that, or to the left and to the right of that, or in front of or behind that, however you want to look at it, but it's not going to be in that area. And I've drawn it rather badly here. Again, the book does it better than I can. But if you have, say, two py orbitals standing straight up next to each other, they can overlap. And the way I've drawn it in the past is just a few lines going from the lobes of the two orbitals from one to the other. But the way it actually looks is something like this, more of a blob shape. And then the two dots here would be the two nuclei. And so you notice there's an unshaded lobe above the plane of the bond, or the sigma bond between the two nuclei. And there's a shaded lobe of the pi bond below the plane of the sigma bond. And both of those together count as one pi bond. And this pi bond would be formed by the pi p bonding molecular orbital. At the same time, you can also have electrons, or you can also have the possibility that p orbitals will meet up out of phase. Notice how both of the shaded portions were on the bottom up above here. It's possible that they might be out of phase, so that the shaded portion is on the bottom here and on the top here. And if they meet up like that, that's destructive interference, and that results in an anti-bonding molecular orbital. And that ends up looking something like this. Badly drawn, yes. That's on page 435 or 445 in the textbook, if you want to look at a good rendering of it. But the point is, anyway, that the density of the electrons involved in this anti-bonding molecular orbital, the density is not between the two atoms. It's outside of the two atoms. And so there's no bond here. And that's why having anti-bonding electrons is bad if you want to form a bond. And the same would be true for the pz orbitals, only the pz orbital would be oriented this way, perpendicular to the py orbital, but it works the same way. The pi bonding and pi anti-bonding orbitals are degenerate with each other, just like the p atomic orbitals are. And that is, they're the same size and the same energy as the same shape. That is, the pi bonding orbitals are degenerate with each other, and the pi anti-bonding orbitals are degenerate with each other. But remember, the pi anti-bonding orbitals have same size and same shape as the pi bonding, but much higher energy for the anti-bonding. And one thing to keep in mind as we're looking at molecular orbitals is that the total number of molecular orbitals will be the same as the total number of atomic orbitals that go into making them. So if we're talking about two atoms next to each other, each of them has 3 p orbitals on it in its valence shell, px, py, and pz. So that's a total of 6 p orbitals altogether. Well, you're going to get 6 molecular orbitals when they come together to form, or to try to form, a bond. You're going to get sigma px and sigma star px. That is from the end-to-end overlap. You're going to get pi py and pi star py. And you're going to get pi pz and pi star pz. So 3 bonding and 3 anti-bonding molecular orbitals, that's 6. Okay, so same number. The way that we actually visualize two atoms coming together to form a bond, or not form a bond, as the case may be, is through what are known as molecular orbital energy diagrams. And in this, we can not only see how the atomic orbitals come together to form molecular orbitals, whether bonding molecular orbitals or anti-bonding molecular orbitals, we can also look at their relative energies, because we tend to draw it from the bottom up, lowest energy to highest energy. Okay, so the way you usually arrange these is with the atomic orbitals of one atom on the left side of the page, and the atomic orbitals of the other atom on the right side of the page, and then the molecular orbitals will be in the middle. In this way, you can sort of draw lines to show how the atomic orbitals come together and form the molecular orbitals in the middle. Each, generally, to simplify things, we draw orbitals as just, little short horizontal lines like that. And if there's an electron in it, we draw it like that. And if there's 2 electrons in it, we draw it like that. But the line itself is the orbital. And the line itself, if there's nothing on it, then that just means that the orbital is empty. So as before, each molecular orbital can still hold a maximum of 2 electrons, just like atomic orbitals. Sorry. Each pair of atomic orbitals that is an atomic orbital from one atom and an atomic orbital from the other atom, will come together to form two molecular orbitals. One of them will be a bonding molecular orbital and the other will be an anti-bonding molecular orbital. So basically, two atomic orbitals come together from two atoms, and when they meet, they form two molecular orbitals, one of which is higher in energy and one of which is lower in energy. And the lower energy one is the bonding molecular orbital, and the higher energy one is the anti-bonding molecular orbital. We often use dotted lines to trace out where the atomic orbitals go to form molecular orbitals. Although I tend to use straight lines rather than dotted lines just because it's easier. But the book uses dotted lines for that. The electrons distribute into the molecular orbitals according to the Aufbau principle. That is, the electrons go to the lowest energy position available, and they will then, they will fill orbitals one at a time. If the orbitals are degenerate, then the electrons will occupy them singly before they start doubling up. And if you fill up one level of energy, then the next electron goes in the next lowest position available. Okay, electrons in the same orbital still have to have opposite spins. So that would be like this, one up, one down, if they're going to be in the same orbital. If they're going to occupy separate degenerate orbitals, then you would draw them pointing the same way. Okay, and we can also write molecular electron configurations, just like we wrote electron configurations for atoms before. The molecular electron configurations are a little more complicated. Oh boy. And because they include the designation of whether it's a sigma molecular orbital or a pi molecular orbital, and also whether it's a bonding or anti-bonding molecular orbital, and also the type of atomic orbital it comes from. So just to look at an early example, we could take B2 plus. That is two boron atoms bonded together, missing one electron. The boron is atomic number 5, meaning each boron atom has 5 electrons. And if you put two boron atoms together, you would expect to have 10 electrons. But this is B2 plus, so one of the electrons is missing. And so that means this structure is going to have a total of 9 electrons. And we would draw the diagram like this. Start with the s electrons. Now, we don't usually bother with the inner shells of electrons. We only do the valence shell because the inner or core electrons normally have completely filled orbitals. And in those cases, any bonding electrons will be canceled out by anti-bonding electrons, and it won't amount to anything as far as forming a molecule is concerned. So we only include valence electrons because that's where the bonds form, if anywhere, anyway. Okay, so we've got on one side, we're going to have a boron atom, but on the other side, we're going to have a B plus ion because one of these boron atoms has to be missing an electron. And we could have done it the other way around if we wanted to with B plus on the left, but I just decided to put the B plus on the right. So the electron configuration for boron would be one s2, 2s2, 2p1. That's 5 electrons. You can also get it from the fact that boron is in period number 2. So it's going to have a valence shell of 2s2, and its boron is the first element in the p block in the second period. So that's 2p1. And then, of course, it's going to have the 1s2 core electrons below that. Okay. The electron configuration of B plus would be 1s2, 2s2, and that's it because it's missing that last electron. Okay, so for the 2s orbitals, each boron, that is the boron atom and the B plus ion, will have 2 electrons. So the 2s orbital of the boron on the left would be this line right here, and the 2s orbital of the B plus ion on the right would be this line right here. And each of them has 2 electrons. When these atomic orbitals come together to form a molecular orbital, they split into 2 molecular orbitals, which are right here in the center. The lower energy one is the sigma 2s bonding orbital, and the higher energy one would be the sigma star 2s anti-bonding orbital. We've got 4 electrons to go into these molecular orbitals, and so we start filling in electrons at the lowest energy position, which would be the sigma 2s bonding molecular orbital. So we fill in 1, 2, and then the next lowest energy position would be the sigma star 2s anti-bonding orbital. So the next 2 go there. Now, in terms of p electrons, one of the borons has 1 single p electron in the second shell, and the other one doesn't even have that. And so when the p orbitals from the 2 atoms come together to form molecular orbitals, you get a more complicated splitting than with the s atomic orbitals. You have the sigma bond that can be formed, or the sigma molecular orbital that can be formed between the p orbitals, being the lowest energy molecular orbital. Then you have the pi bonding orbitals that can be formed from the p orbitals of the atoms, being the next lowest energy. And remember, there are 2 of those. That's why I've drawn a separation between the 2 horizontal lines here. Then the next lowest energy would be the anti-bonding pi star molecular orbital formed from the 2 p electrons. And the highest energy of all would be the sigma star anti-bonding molecular orbital formed from the 2 p electrons. Notice that the total number of orbitals here is 6 either way. Looking at the atomic orbitals, you've got 3 orbitals here, 3 orbitals here. That's 6 orbitals altogether. Looking at the molecular orbitals in the center, you've got 1, 2, 3, 4, 5, 6. So they're all there. It's just a question of what order they go in and where the electrons go. In this case, there's 1 single electron in one of the p orbitals in one of the boron atoms, and that 1 single p electron will come down to the lowest energy position available, which is the sigma 2p bonding orbital. Okay. And looking at this, we haven't gotten to bond order formally yet, but just looking at this diagram, the fact that we have more electrons in bonding orbitals than we have in anti-bonding orbitals would tell us that this molecule B2 plus, or ion rather, would form, but the bond would be weak, and so it wouldn't be very stable. Because we've got a total of 1, 2, 3 electrons in bonding molecular orbitals, and we've got only 2 electrons in anti-bonding molecular orbitals. So it's kind of a close call, but bonding does win, but only by a little bit, and that's what makes the bond fairly unstable and why the molecule isn't found very often. Okay, that brings us, like I said, to bond order. The bond order is ultimately what explains why some bonds form and others don't. And we also often find that bonds form between atoms that we don't normally expect to form bonds with each other, just because we don't encounter them that way very often. But all we're really finding here through bond order is that it's possible for that bond to form. That doesn't really tell us how often it actually happens, because there can be competing bonds that are more likely to form. Okay, so if the number of electrons in bonding molecular orbitals is greater than the number of electrons in anti-bonding molecular orbitals, then the bond will form, although it may be weak. If you end up with the same number of anti-bonding electrons as you have bonding electrons, then the bond doesn't form. You normally won't encounter any situations where you have more anti-bonding electrons than bonding electrons, because that would require the atom to be in an excited state. In other words, there are electrons in higher energy positions than they should really be in, with vacancies in lower energy positions. And that, again, is an excited state. And we don't normally deal with those when we're dealing with bond order. Mathematically, bond order is equal to 1/2 of the total of number of bonding electrons minus the number of anti-bonding electrons. And the reason it's done like this with 1/2 is that it makes the number meaningful. It makes the result meaningful. So if you basically take bonding electrons minus anti-bonding electrons and divide it in half, then if the answer to the bond order is 1, that means that not only does the bond form, but it's a single bond. If the bond order ends up being 2, that means the bond forms and it's a double bond. If the bond order is 3, that means that the bond forms and it's a triple bond. If the bond order is 0, that's what you would get if you have an equal number of anti-bonding and bonding electrons. The bond order would be 0, and that means the bond does not form. It is possible to have intermediate bond orders. One example would be in cases where resonance exists in a molecule. You have those delocalized electrons that can move around between atoms. And that would be like in a case where you have a double bond that can switch back and forth between two sets of neighboring atoms. And you effectively have a bond order of, say, 1.5, like halfway between a single bond and a double bond. Well, that is possible, and you can determine that through bond order. If it comes out to be 1.5, then that's a pretty good indicator that resonance is probably involved. Also, bond order can tell you the relative strength of a bond, because as the bond order goes up, the number of bonds goes up and the strength would increase. So, triple bond is stronger than double bond, which is stronger than a single bond, and 3 is greater than 2 is greater than 1. So you can use the bond order as an indicator of bond strength. Okay. Looking at some bonding in diatomic molecules, sorry, homonuclear diatomic molecules, to keep things relatively simple. You can actually do heteronuclear diatomic molecules too, but this book chooses not to. Fortunately, I have no problem with that, because in those cases, the diagrams end up looking really weird, because if you got two different atoms, then the s electrons, for example, would have different energies. So you have to draw this line and this line at different levels, and then the diagram gets all lopsided and weird looking. So anyway, so simple stuff, fortunately. Starting with H2, hydrogen. Each hydrogen has an electron configuration of 1s1. So you draw your s orbitals for the two hydrogen atoms and put one electron in each of them. And then you draw the s atomic orbitals coming together to form the sigma molecular orbitals, the lower energy one being the sigma bonding 1s molecular orbital, and the upper one being the sigma star anti-bonding 1s molecular orbital. And if you've got two electrons to deal with, then they both go into the bonding molecular orbital. Your bond order would be 1/2 the number of bonding electrons minus anti-bonding electrons. So that's 1/2 of 2 minus 0, which is 1, which means the H2 molecule does exist and it has a single bond, which we know. That's confirms something that we already know, so that's good. The molecular electron configuration would be basically listing out the molecular orbitals that have electrons in them, and then using a superscript to indicate how many electrons are in each molecular orbital. So in this case, it would be sigma 1s parenthesis 2, because there are 2 electrons in the sigma 1s bonding molecular orbital. Another one would be He2. Now, we already know that helium is found as individual atoms, and also that helium is a noble gas, which doesn't normally want to form bonds. Actually, helium never wants to form bonds, not even under the most extreme circumstances. So it will be something of a surprise if the bond order here is anything other than 0. But we'll check it just to be sure. You've got the 1s orbital of 1 helium with 2 electrons in it. And sorry, that's not 2s, that's 1s. 1s orbital of the other helium atom with 2 electrons in it. And when they meet to form molecular orbitals, you have one sigma 1s bonding molecular orbital and a sigma 1s sigma star anti-bonding orbital. And you've got 4 electrons. So 2 electrons go into the bonding molecular orbital and 2 electrons go into the anti-bonding molecular orbital. And you end up with a bond order that's 1/2 number of bonding electrons, which is 2, minus number of anti-bonding electrons, which is 2. So 1/2 of 2 minus 2 is 0. That means no bond. And this molecule does not form. The molecular orbital electron configuration, if you wanted to do it, I mean, there's not much point in writing out an electron configuration for something that doesn't exist. But anyway, this configuration here would correspond to sigma 1s2, sigma star 1s2. Okay. Next, the next atom on the list is lithium, atomic number 3. And so we can see, does dilithium actually form? And we can look here at the valence shell. Remember, the inner shell electrons are not involved in bonding, so we're really only concerned about the valence shell here. The electron configuration of lithium is 1s2, 2s1. You can tell that it ends in 2s1 because it's in the second period, and it's the first element in the s block in the second period. So 2s1, that's the valence shell. All right, so 2s orbital on one lithium has a single electron. The 2s orbital on the other lithium has a single electron. And when they meet to form molecular orbitals, you get a sigma 2s. Now, notice this time it's sigma 2s bonding orbital and a sigma star 2s anti-bonding orbital. You've got 2 electrons in total in the valence shell for the molecule as a whole. And so both of those 2 electrons go into the lowest energy orbital available, which is the sigma 2s bonding orbital. And if you want to look at bond order, the bond order is 1/2 of the number of bonding electrons, which is 2, minus the anti-bonding electrons, which is 0. So 1/2 of 2 is 1. So single bond, this molecule does form. Dilithium does exist. Although you don't actually find it very often because metals like lithium tend to be attracted to other metals in 3 dimensions. And so a metallic bond is essentially a bunch of nuclei of the metal. So in this case, lithium, that are sort of fixed in place with a sea of mobile valence electrons around them. And so Li2 does exist, but you won't actually find it very often. What you usually find is Li, like 10 trillion all stuck together. Anyway, the number of bonding and anti-bonding atom or electrons that you have to subtract are only the ones from the valence shell. We don't need to do anything with the inner shell electrons from the shell number 1 for lithium because they would cancel out. Like we saw here, if all of the orbitals for shell number 1 are filled, then they just end up canceling each other out. It's only the valence electrons that really matter. And as we saw here with He2, sometimes the valence electrons end up canceling each other out also. And that just means that that's a case where the bond doesn't form. The molecular orbital electron configuration in this case would be sigma 1s2 if you wanted to include the core electrons, but the valence shell would be, sigma 1s2, sigma star 1s2 if you want to include the core electrons. But if you just want the valence electrons, then it would be sigma 2s2. That's the valence electron configuration. Okay, well, we're kind of a little over time, but we actually near the end of the chapter also. But I think I will cut this off and we'll do a very short section C right after this. Okay, I will be right back.